Today we're going to explore one of the most fascinating phenomena in materials science: how brittle ceramics that shatter easily at large scales can actually bend and deform plastically when you shrink them down to the nanoscale. Let's start with what we normally think about ceramics. When you drop a ceramic coffee mug on the floor, what happens? It shatters into many pieces. This is the hallmark of brittle behavior. The ceramic mug has many internal flaws and microcracks. When you apply stress, these cracks propagate catastrophically, and the material fails suddenly with almost no plastic deformation. Think of ceramics like glass. They can be very strong and hard, resisting scratching and wear. But they have essentially zero ductility. One crack starts and boom, total failure. But why are ceramics so brittle in the first place? The answer lies in their atomic bonding and their inevitable defects. Ceramics typically have ionic or covalent bonding. These bonds are strong but directional and not easy to rearrange. Unlike metals, where dislocations can glide easily, ceramic crystal structures resist dislocation movement. But here's the real killer. Every real material contains flaws. Small cracks, pores, impurities. These are called Griffith flaws after the scientist who first analyzed them. Let me introduce you to one of the most important equations in fracture mechanics, the Griffith criterion. The fracture stress sigma F equals the square root of 2e gamma divided by pi circa. Let me break down what each term means. Sigma F is the fracture stress, the stress at which a crack will propagate and cause failure. E is the Young's modulus, which measures the material's stiffness. Gamma is the surface energy, the energy cost of creating new crack surfaces. And C is the crack length. This is the critical parameter we're going to focus on. Notice the inverse square root dependence on crack length. As the crack gets longer, the fracture stress drops dramatically. Longer cracks mean easier failure. Here's a material under tension with a crack of length 2c. The crack concentrates stress at its tip. When the stress intensity reaches a critical value, the crack propagates catastrophically. Let's do a numerical example with alumina, which is aluminum oxide, a common engineering ceramic. For alumina, the Young's modulus is about 400 gigapascals. The surface energy is approximately 1 joule per square meter. Let's say we have a typical flaw size of 1 millimeter, which is 10 to the minus 3 meters. Plugging into the Griffith equation. Fracture stress equals the square root of 2 times 400 times 10 to the 9 times 1, divided by 3.1, 4 times 10 to the minus 3. This gives us about 450 megapascals. That's a decent strength, but not amazing. Now here's the key question. What happens if we shrink the flaw size? What if, instead of 1 millimeter defects, we only have nanometer scale defects? Let's recalculate with C equals 10 nanometers, which is 10 to the minus 8 meters. That's 100,000 times smaller. Same equation, but now C is 10 to the minus 8. The square root of this much larger number gives us a much higher fracture stress. We get about 140 gigapascals. That's enormous. That's approaching the theoretical strength of the material. Notice that by reducing the flaw size by a factor of 100,000, the strength increased by about 300 times. The square root relationship is key here. So now we understand that smaller flaws mean higher strength. But there's another crucial effect at the nanoscale: statistical volume effects. Here's a fundamental principle. Larger volumes contain more defects. It's a statistics game. The probability of finding a crack of a given size increases with the volume of material. So here's a question. What happens when you make a ceramic nanowire that's only 50 nanometers in diameter? Let me answer that. Imagine a ceramic nanowire that's only 50 nanometers in diameter. The entire volume is so tiny that it's statistically unlikely to contain any large defects. The probability of finding a crack larger than a certain size drops exponentially as the volume decreases. In a nanowire, there simply isn't room for large cracks. If there are no large flaws, the material can approach its theoretical strength. And at these stress levels, something remarkable happens. At very high stresses, even in ceramics, dislocations can nucleate and begin to move. Remember, ceramics resist dislocation motion, but they don't make it impossible, especially at extremely high stress levels. When dislocations can move, the material can deform plastically rather than fracturing. This is the transition from brittle to ductile behavior. This isn't just theory. Experimenters have actually bent ceramic nanowires inside electron microscopes and observed plastic deformation. They took alumina nanowires, applied bending forces, and watched them curve smoothly without shattering. Materials that are legendarily brittle at the macro scale become ductile at the nanoscale. Researchers have reported elastic strains of 5 to 8% in alumina nanowires before permanent deformation. Bulk alumina would fracture at strains of 0.1% or less. So what's the critical size below which this transition occurs? It depends on the material and the defect distribution. For many ceramics, the transition from brittle to ductile behavior occurs when the diameter drops below about 50 to 200 nanometers. Below this size, flaw-free volumes become probable. Let me give you an analogy. Think of a chain made of many links. The chain is only as strong as its weakest link. If you have 100 links, chances are at least one is defective. But if you only have 2 links, both might be perfect. A large piece of ceramic is like a chain with millions of links. Statistically, some of them will have large flaws. The material fails at the weakest point. A nanoscale ceramic is like a chain with only a few links. The probability that all of them are strong and flaw-free becomes significant. Now let's talk about the competition between two failure mechanisms, crack propagation and dislocation motion. Here's an important question. Why does plastic deformation through dislocations win out over crack propagation at the nanoscale? Let me explain. Crack propagation requires a pre-existing crack. If there are no large cracks in your nanowire, this mechanism is suppressed. But dislocation nucleation can occur homogeneously from the perfect crystal lattice when the stress is high enough. At nanoscale, flaw-free samples reach these ultra-high stresses. There's a theoretical maximum shear stress that a perfect crystal can sustain before dislocations nucleate. It's related to the shear modulus. The maximum shear stress is approximately the shear modulus G divided by 10. This is the theoretical strength for dislocation nucleation. For alumina, the shear modulus is about 150 gigapascals. So the maximum shear stress is about 15 gigapascals. If you can reach stresses in this range without triggering crack propagation, dislocations can nucleate. In flaw-free nanowires, the absence of stress concentrators means you can actually reach these theoretical stress levels. That's when ductility emerges. Here's another analogy. Think about graphite pencil lead. A thick piece of graphite snaps easily when you try to bend it. But if you make it really thin, like a strand of fiber, it becomes surprisingly flexible. It's the same material, just at a different size scale. The thinner piece has fewer defects and can bend more before breaking. So what are the implications of this nanoscale ductility in ceramics? It opens up exciting possibilities. One application is ceramic nanocomposites. By incorporating ceramic nanostructures into a matrix, you can create materials that combine hardness with toughness. Another application is flexible ceramic electronics. Imagine electronic devices with ceramic components that can bend and flex without breaking. Nanoceramics can also be used in energy-absorbing applications, where you want a hard material that won't catastrophically fail on impact. Here's a practical question. Can we somehow scale up this behavior to make bulk ceramic materials that are ductile? Unfortunately, the answer is challenging. The problem is that it's very difficult to make large volumes of material that are completely free of defects. As soon as you increase the size, defects creep in. However, by nanostructuring bulk ceramics, creating materials with nanoscale grains, or incorporating nano-reinforcements, we can improve their toughness significantly, even if they don't become fully ductile. Let's look more carefully at the mathematics of how strength scales with size. The probability of failure can be modeled as 1 minus e to the negative v over v naught, where v is the volume, and v naught is a characteristic volume related to defect density. As the volume 5 decreases, the probability of containing a critical defect drops exponentially. This is the statistical basis for the size effect. This leads to a power law scaling of strength with volume, sigma proportional to v to the negative 1 over m, where m is the Weibull modulus that characterizes the defect distribution. There's one more important effect at the nanoscale. Surface effects become dominant. When you shrink down to nanoscale, a large fraction of the atoms are at or near the surface. Surface atoms have different bonding environments than bulk atoms. Surface stress and surface energy effects can actually suppress crack nucleation. The surface atoms create a kind of compressive layer that resists crack opening. The surface stress scales as 2 gamma over r, where r is the radius. As r decreases, this stress increases, providing additional strengthening. Let me summarize the key points about the brittle to ductile transition in nanoceramics. First, Griffith fracture theory tells us that strength increases dramatically as flaw size decreases, with an inverse square root dependence. Second, small volumes have statistically fewer defects, and the defects that do exist are smaller, so the material is stronger. Third, when ceramics are strong enough to reach very high stresses without fracturing, dislocations can nucleate and move, enabling plastic deformation. Fourth, below a critical size of roughly 50 to 200 nanometers, many ceramics transition from brittle to ductile behavior. This phenomenon beautifully illustrates how the same material can behave completely differently depending on its size scale. Size truly matters in the world of materials.